And our next talk is actually remote, right? And I'll let the technical help bring it on screen. This talk is by Stefan Dolan from Jane Street. It's about lifetime dispersion and generational GC, and it's an intellectual abstract. Where is this there? It's right there. Ah, well, there he is.
Thank you. So this talk is lifetime dispersion and generational GC. The starting point here is two very well-established facts about programs. And these really are empirical facts. They have been confirmed widely across many different programs, many different language implementations, and even many different programming paradigms, functional, imperative, object-oriented, and so on. The first one is the generational hypothesis, which has a couple of versions, but it's often phrased as something like, most objects die young, or the objects which are allocated recently are the most likely to become unreachable soon. And actually, as we'll see in a couple of slides' time, those are not quite equivalent. But the general idea is that most of the garbage is young objects. And the second well-established fact about programs that this talk is about is that generational garbage collection is a good idea. It works pretty well. This idea of separating the heap, logically or physically, and having a separate nursery generation of the recently allocated objects, which is collected earlier and more frequently than the heap as a whole. And this turns out to improve system performance across a wide range of programs. So these are both fairly well established, and I'm not planning to contradict either of them. But what I plan to focus on here is the connection between the two properties. In fact, as we'll see, the generational hypothesis, as stated there, does not actually imply that generational garbage collection is a good idea. But I think both of these things are true, but that version of what the generational hypothesis is not really a very good explanation of why generational GC is so effective. So I'm going to give a couple of examples to explain what I mean here. Where we can compare the different versions of the hypothesis and whether generational GC actually works. So the first one of these is a very simple program that's just a single big queue. In this queue, most objects, this program inserts values into a queue, allocates new values, inserts them into a queue, and deallocates them from the far end of the queue and discards them. So every object lives exactly the same lifetime. They all live just long enough to traverse the queue. They all survive until they get to the end, until they are dequeued. None of them die young. The next unreachable object is not likely to be young, and generational garbage collection does not apply. This is not a generational program. If you try to run generational garbage collector with this program, then you'll find that it just makes performance worse. The extra overhead of bookkeeping, remembered sets, moving things from heap to heap, just costs, because identifying the young values in this program does not help you. So if we modify this program slightly, and we discard 25% of the allocations immediately rather than pushing them through the queue, then we find, so in this version of it, 3/4 of the program, 3/4 of the allocations still traverse the queue as before, 1/4 are just dropped on the floor immediately. Now in this program, it still doesn't satisfy either version of the generational hypothesis. Most objects do not die young, most objects live for the length of the queue. And the next object to become unreachable is not the most recently allocated one, typically. 25% of the time it is, but 75% of the time the next object to become garbage is whatever's fallen off the back of the queue, which is in fact the oldest object in the system. Yet, on such a program, generational GC will tend to be effective. A young generation, even of a very, very small size, like enough to hold one object, will manage to find 25% of the garbage of this program. And if the young generation is very small, then the overhead of doing so is just one object's worth. So it's easily worth the cost. So generational GC is effective on this program, but its effectiveness is not explained by the generational hypothesis. But I made a slightly stronger claim earlier. I claimed that the generational hypothesis did not imply that generational GC was effective. So to falsify that idea, I'm going to need to find an example where the generational hypotheses are true and yet generational GC is not effective. And so an example program along these lines was actually given by Baker back in 1993, and it's an exponentially distributed object lifetime. So in this program, we're still going to keep allocating new objects and putting them into this big queue, except instead of dequeuing them like a normal queue, we're going to select a random object to dequeue each tick, and then remove a random object from the queue and discard it. So any given object has a fixed probability of being the one chosen at each tick, and that means that the lifetime of an object, which is the number of ticks that it survives before getting deallocated, will be exponentially distributed, or theoretically, or more technically geometrically distributed, but exponential is the continuous approximation. And in this program, generational GC is not a good idea. Every object in this program is equally likely to be dequeued next, to be discarded next. So there is no benefit to identifying a particular region of the heap as the nursery, because it is producing garbage at no better a rate than any other part of the heap. However, this version of the generational hypothesis does actually distinguish the two phrasings. It's true in this program that most objects die young, but it's not true in this program that the next unreachable object is likely to be young. Because most objects die young, but also each object is equally likely to be the next one to die. So we can modify this program slightly and get a version where instead of choosing uniformly at random which object to remove from the queue, we add just an arbitrarily small bias. We're very, very slightly more likely to select an object from the start of the queue, or towards the start of the queue. So this bias is so small that it has essentially no effect on the performance of the program as a whole. So generational GC remains as ineffective as it was in the previous example. And yet, that tiny bias is enough to make the second version of the generational hypothesis also come out as true. The next object is slightly more likely to be young than to be old. And still, most objects die young, because in an exponential distribution, the median is less than the mean. More than half of the objects do live less than the average lifetime. So I hope these examples go some way towards explaining why I think that the generational hypothesis is, while has been shown to be generally true, it's not a great explanation of why generational GC works. So that leads to the two questions that this work raises, which is, if it's not most objects die young, what property exactly is it that makes generational GC effective? And the second question is, why does this property typically tend to hold in practice? It's been quite widely confirmed empirically that the generational hypothesis does actually hold for a lot of programs. And why is that? What is making most programs be generational? So the answers to these two questions are based around a new metric that measures generationalness of a program more directly. So this new metric G has a number of advantages over the standard generational hypothesis. First, it's a quantitative measure. It goes from 0, which is a completely non-generational program, like the single queue of the first example, up to 1, which is a program where a small proportion of the objects are very, very long-lived tenured objects, and everything else is immediately discarded. So that's a maximally generational program. And it gives every program just a number between 0 and 1 that quantifies how generational it is. It's a property of program behavior. So, of course, it may depend on the lifetime distribution of a program may, of course, depend on its input as well as its text. So it's not just a static property of program source code, but the point is that it doesn't depend on GC implementation choices. So it's not a metric like the amount of garbage collected by a semi-space collector with a 4 megabyte nursery. It's a property intrinsic to the program, unrelated to how you choose to implement the garbage collectors. And as explained in detail in the paper, it's sufficient. Its high value of this metric is sufficient to show that generational GC is effective. There's a simple model of a generational collector in the paper. It has a number of caveats because it's a very simple paper model, but there's also proof showing that under this model, any program with a large enough G will have its performance improved by a generational collector. And the answer to the second question of why generational collection typically helps in practice is this result about composition. Unlike the standard generational hypothesis, this version with the metric G is compositional in that we can say something about a composed program by knowing what this metric says about its parts. And in particular, composing a program out of multiple parts tends to increase G, giving some explanation for why large programs tend to exhibit generational behavior. So what is this actual metric? Well, it's based on lifetime dispersion. So statistical dispersion measures how spread out a distribution of a variable is. The variable in question here is the lifetime of a random object. So the key idea here is that we're focusing on the distribution as a whole. It's not a property about just the young end of the distribution. It's about saying that there is a large diversity of different lifetimes in the program. Not just that lots of them are young, but that there's a wide range of them. And the exact way that this is being quantified uses some statistical tools that were developed for economics. The Lorenz curve is a completely generic piece of stats that you can use for any variable, but it was introduced for economics, and it is typically used to measure income inequality or wealth inequality. So it's this curve going from 0 to 1. It's always increasing and it's always convex. And along the x-axis, it shows the percentile rank of a variable. And along the y-axis, it shows what fraction of the total or even what fraction of the mean of that variable is achieved by that percentile. So that point that's labeled on this graph at 0.6, 0.2 is interpreted in economics as saying that this represents that the bottom 60% of households are receiving just 20% of the total income. So if there's perfect equality, then this tends to be a 45-degree line going from 0 to 1. And if there's perfect inequality, there's just complete inequality with all of the income going to a single household, then this will look like a right angle going all the way along the x-axis, then turning upwards, going all the way up the y-axis. So it turns out this tool is an excellent way of analyzing garbage collector behavior as well as economics. And that same graph, if the variable is not income but object lifetime, can be interpreted as saying the youngest 60% of allocations occupy only 20% of the memory currently in use by live objects. So that interpretation is not a completely trivial step. The details are in the paper. The slightly fiddly bit is that we're taking a variable about lifetimes and we're making a statement about, so that's a time metric, and we're making a statement about space usage. And to connect those two, we use Little's law from queuing theory, which tells us that the average lifetime is going to be proportional to the average heap size, thinking of objects in memory as a form of queue. So then we can, having introduced the Lorenz curve, we can see the actual metric that I'm proposing here for generational collection, which is, again from economics, the Gini coefficient. So this is a number from 0 to 1, and it measures inequality, and it can be derived directly from the Lorenz curve. So it measures the area under the Lorenz curve, except it's scaled so that 0 is complete uniformity and 1 is complete inequality. And generational GC will become effective when G gets high enough. So if we look again at the Lorenz curve, then we measure the area under the curve, but actually G is defined as 1 minus 2 times the area under the curve. So that means when the area under the curve is large, it's a half, is the biggest it can be. That means G is 0. And when it's tiny, that means G is close to 1. So when G is close to 1, the area under the curve must be very small. And if the area under the curve is very small, then since the curve is increasing and convex, that basically means that the curve has to be tucked into the bottom right corner. And it means there will be some point along the curve close to the bottom right corner. And such a point will always represent some percentile, so that the youngest X% of allocations occupy only a small portion of the live heap. And that gives us a good generation size. If we take a generation big enough to contain only that proportion of the live heap, then despite being small, it will still be able to collect a large proportion of the total allocations. So that's a very informal argument for why a high value of the Gini coefficient will be sufficient to make generational garbage collection work. There's a much more detailed argument in the paper against a concrete model. With a number of caveats, it's a very simple model, but nonetheless a concrete model of how generational garbage collector works. So the final part of it is the explanation of why this tends to increase with composing larger programs out of smaller. So larger programs are modeled here as mixture models. So that's the distribution of lifetimes is a combination of the distribution of lifetimes of the subprograms. This works. This is a good model for parallel composition, where the objects have unrelated lifetimes, and it's a good model for sequential composition of a pipeline of stages where each stage is allocating fresh objects to pass on to the next stage. I point out it's not a good model for sequential composition where objects are being reused all the time. If each stage in the pipeline is just passing the same object along, then you'll find that the arguments here don't apply. But at least when different subprograms are allocating different objects at different rates, then the argument here will apply, and we'll find that the composing larger programs out of smaller tends to increase G. In two different ways, both that it's bounded by the G of its parts, and also it's bounded by how different the parts are. If a composition of two non-generational parts that are sufficiently different will still be generational. So in summary, I'm arguing that a high Gini coefficient is a better version of the generational hypothesis than the standard one. It's quantitative, it's a thing we can actually measure and compare between benchmarks. It's not dependent on a particular implementation strategy. It composes better, and it's actually sufficient to prove that generational GC works. So thank you, and think of some time for questions.
Yeah, thank you. So it's a great example of an intellectual abstract. Thank you for the presentation and work. So a question?
Yeah. Great talk. I really enjoyed that. Steve Blackburn, Google and Australian National University. Great talk, Stephen. Really enjoyed that. Just two fairly simple questions, I guess. Oh, first of all, I should say that this is, I'd really love to integrate this into our detailed analysis of the Da Capo benchmarks, or any other benchmarks for that matter, and just have that as public knowledge about what the G values are for the different workloads. It's be quite useful. But more specifically, you mentioned the point about time and Little's law and so forth. Oftentimes we measure time in memory management in bytes allocated rather than on the wall clock, which perhaps would make that easier. That's one part of the question. The second part of the question was the phasic behavior. That is to say, I haven't seen your paper yet, so I'll look forward to reading it. But I just wondered if you'd given any thought to, or you'd studied programs that change phases with respect to this metric, or whether this analysis allows for people to reason about how the G factor might change as a function of time.
So first of all, I'd love to see measures of these in the Da Capo benchmark suite. So a limitation of the analysis in the paper is that I'm just assuming steady state. I like assuming a program with a single phase. That's partially where the Little's law thing is coming in that that's the thing that says in the steady state the average lifetime is proportional to the average heap size, and that's kind of assuming that an average heap size is a thing that exists and is constant. So I think this, like, it does make sense to talk about this G value changing over time, but I have to do a bit more maths to make that idea completely make sense.
Okay, hi. So it's Eres Petrang from the Technion. First question, when you say that it was not good to use generations, did you actually experiment with programs, or you just believe it will be like that? And second part of the question is there any tool that can help measuring the G value, the Gini value on a program that I have?
Okay, so first of all, it's no. This is a bunch of maths rather than empirical measurements. So for the first program, I think generational GC will definitely be ineffective in that every generational GC is ineffective when there's 100% promotion rate. You're paying all of the bookkeeping cost, but you're not getting any of the benefit. But I do want to be clear that this is like the intellectual abstract property of this paper is that it is just a model. It's not been validated or anything against an empirical, against an actual implementation. So for actually measuring this precisely over programs, it's fairly so it's very easy to compute G given knowledge of the distribution of object lifetimes. That can be somewhat hard to get. It's fairly easy to get an over approximation of this by trying garbage collection at different heap sizes to see how well it collects. But there is some work on particularly the Merlin trace tool to give precise information about object lifetimes. And as future work, I'd really like to hook this up to Merlin or one of its descendants to actually produce precise information about the G coefficient.
Thanks very much. Yeah, thanks, Jeremy Singer, Glasgow University. Thanks, Stephen. Lovely talk. I really like the idea of kind of mathematical and economic models for memory management. My question is, does your analytical model assume that all allocations are equally sized?
No, it doesn't make that assumption, but that's partially because it doesn't really come up very much. So the input to the model is a completely arbitrary distribution of the lifetime of a random byte of allocation. So if objects have different sizes, then you'll find lots of them. Like you will find that the distribution of a lifetime will be represented in proportion to the size of the objects allocated there, but it all just boils down to a single distribution, so the analysis doesn't really care.
Thanks.